All right, here's a video for some notes on series circuits. So we're going to start off with the most important formula you need is Ohm's law. It relates voltage, current, and resistance. That's a one formula that does it all. So you could spend your time writing the three different versions, V equals I times R, or I equals V over R, or R equals V over I. Or what we usually like is I'm more fond of this triangle because then you can just cover up whichever piece you're solving for. Units for voltage are volts, which is capital V. Units for current are amps, capital A. And units for resistance are ohms, or capital omega. There you go. All right, so we are only focusing on one at a time right now, and because it gets kind of confusing if you mix up parallel and series circuits. So, real quick, a series circuit, and you got to get this in your head pretty straight because when we mix in parallel, you got to kind of unlearn these things and switch gears. So, a series circuit is a circuit that has just one path for electricity to flow. Okay, so just one path is what makes it a series circuit. And here are three very important ideas when we're solving series circuits. In a series circuit, the current is always constant. That's super important. That's how we're going to solve most of these problems. Number two, the total resistance equals the sum of the individual resistances. Okay, and we're going to use that to solve a lot too. And then the third part is the total applied voltage equals the sum of the individual voltage drops. This is how we're going to check our answers because this, by the way, is called Kirchhoff's voltage law. And we're going to use this to check our answers pretty often. All right, so let's do a couple examples. All right, first example, we have this pretty simple circuit. So we got a 12-volt battery over here. Don't lick this one. And we got a 20 ohm resistor called R1, resistor 1, a 10 ohm resistor, resistor 2, and a 40 ohm resistor at 3. And you can tell the current's supposed to be going this way, even though we know it's wrong. All right, so our first thing is pretty easy. We're going to find the total resistance. Now, if you remember from just like 20 seconds ago, we said that the total resistance for a series circuit is the sum of the individual parts. So in this case, you don't have to, after this time, I won't write these out all the time, but it is worth looking at once. Since there are three resistors, I know that my total resistance, which I would write R sub T, equals R sub 1 plus R sub 2 plus R sub 3. So these three individual resistances will equal my total resistance. So RT is going to be 20 ohms for resistor 1, plus 10 ohms for resistor 2, plus 40 ohms for resistor 3, aka your total resistance is 70 ohms. Okay, so that was our first answer. So far, so good. Oh, by the way, why is this a series circuit? Because There is only one path for the electricity to flow. If I break it anywhere, the whole circuit's broken. There's no way for electricity to flow. All right, total current. Okay, so if I did my little triangle, VIR, and I blocked off current, I would have V over R. But you got to be kind of careful, because when I'm looking for total current, I want you to actually write I sub T, and it has to equal not just V over R, but V sub T over R sub T. Because you don't want to actually grab like one of the individual resistances and put it in here if we're talking about total resistance. Okay, so in this problem, I already know my total voltage because it's up here. It's 12 volts. And I already know my total resistance because we just found it right there, 70 ohms. You want to make sure you're using whole volts and whole ohms. Don't be using like kilovolts or kilo ohms or mega, anything like that. So if you divide this on your calculator, you get 0.1714 amps. Remember, current is measured in amps. Now I do want to keep this for later. However, I don't want to leave that as my answer because it's less than 1. So I want to move the decimal place over, 1, 2, 3. And it's actually 171.4 milliamps. Okay, so that's my total current. That's my answer. Always leave your answers in nice engineering form. All right, now we can find the voltage drops across resistor 1, resistor 2, resistor 3. Because I told you to remember that voltage is like potential energy. So imagine this is like a stair step that is 12 volts high, and I have to get down all 12 volts eventually. So I can find out how much I'm dropping down here. Think of it like a stairwell. And this is another stairwell. And by the end, you're back to the ground floor. This is more like an elevator that goes up 12 floors. Oh, I just thought of that. That was actually better than expected. Okay, easy peasy. Ohm's law on every one of these. If you want me to find resistor 1, I'm going to cover up the R, and you get V over I. So R1 is really V1 over I1. Okay. Oh, crap. Hold on. Ignore that. I want to find the voltage at resistor 1. So I'm actually solving for V. So I'm going to cover up my V, and I get IR. So voltage at 1 equals current at 1 times resistance at 1. All right, so now, what is current at 1? Well, good news, because we set it over here. We're using all these things, man. This is great. Super important. In a series circuit, current is always constant. So if you know the current anywhere, you know the current everywhere in series. Okay, so I want to use my answer from before on current because it's the same at every spot. However, be careful. Don't use this one. You want to use this one because all of our Ohm's law formulas are based off of whole volts, whole amps, whole ohms. So I want to say 0.1714 amps times my resistance at 1 was a 20 ohm resistor. So if you take your calculator and multiply that out, you're going to get 3.429 volts. I don't have to move the decimal place because that's already between 1 and 999. And we're going to kind of do the same thing on both these. So I'm going to pause my thing. I'm going to do them. You pause them. Do the other two. See if you get them right. And then unpause the video. And you can check. Okay. So if you check these, hopefully you got 1.714 volts and 6.857. Make sure you're using your units. Notice that the current I used every time was the same because in series circuits, current is constant. Now I also want you to notice, think of these as stair steps, and this is how much voltage is being dropped across each one. Does it make sense that the highest voltage drop is across the highest resistance, and the lowest voltage drop is across the resistor with the lowest resistance, and the mediumest voltage drop is the one with the mediumest resistance? And I hope that makes sense, because if you think about it, the purpose of a resistor is to resist the flow of electricity. So it makes sense that the higher the resistance, the more volts will be dropped there because it's slowing down the current. The lower the resistance, the less voltage will be dropped. Now verify Kirchhoff's voltage law, which says the voltage total should equal the voltage drop at resistor 1 plus the voltage drop at resistor 2 plus the voltage drop at resistor 3. It's kind of like in geometry where the part plus the part equals the whole. So we have 12 volts, and I'm checking, does the left side equal the right side? So if I took all these and add them up, you're going to get 12 volts and 12 volts. Sometimes that comes out to be, sometimes it's a little bit off. That's just because rounding. Some people, you round too much, it'll be off by a decimal place, but you can tell if they're pretty much right. All right, quick scientific notation review. Remember this. We got giga, mega, kilo for our big ones. Here's our base units. This is where it all divides. We have milli, we have micro, we have nano. Really, these two on the ends don't happen much. But in engineering, we usually tend to use base units, milli, micro, kilo, mega. If your answer is bigger than 999 or smaller than 1, please convert. And you're just moving in chunks of 3, right? So you're going 3 spaces, 3 spaces, 3 spaces. Okay, so now for our last example here. Oh, not our last example. I'm going to pause and start this one up. Okay, same deal here. If you ask me to find IT, I draw my little triangle. Cover up my I, and it's V over R. So IT is VT over RT. And now I realize I need to find, I know my total volts, I need to find my total resistance. So I'm going to pause and do that. All right, so I found total resistance by adding them up. Notice they were kilo ohms, but I wrote this answer here as 8,000, not 8 kilo ohms, because when I use these formulas, when I use Ohm's law, I have to use regular ohms. So, this is my answer, but I want to translate that to 1.5 milliamps before I circle it for total current. Now I can do the total voltage on each, the voltage drop on each part, which would be like V1 equals I1 times R1. And you're going to do that again. Each time I'm using the 0.0015 amps and not the milliamps. And I'll use 1,000 ohms instead of 1 kilo ohm from up above. And you'll see you get 1.5 volts. Okay, I'm going to pause, do the rest. You do the same. See how it works out. Okay, so if you check it out, I did the same thing again, always using the full ohms, the full amps, and I get full volts, so I don't have to move those around. And when you go and check, I didn't have to do it a second time, it matched that. You go and check, and 12 volts equals 12 volts. Awesome. Now on to the last problem. All right, so if they ask me to find the voltage drop across R2, I would have V2 equals I2 times R2. Now, I don't know either of those yet, but I can find R2 real quick by using the total and subtracting all the other ones, and I can get R2 to put here, right? And then I can find V total by taking, or your current total equals your voltage total divided by your resistance total. Okay, and notice when I plug those in, I didn't turn either of those into our engineering notation because I only care about the end answer. All right, now I'm going to do the last one. You should pause it, see if you can do it on your own. Okay, they're asking for VT, which must equal IT times RT. And we got to add up our resistances on each part. We get 5,000 ohms resistance, and then they gave me 5 milliamps, which I moved the decimal 1, 2, 3 over, and we get 0.005 amps. Then I just got to plug it in and see what happens. And our total is 25 volts, which is a really powerful battery. All right, hope that makes sense. Soak it all in. We'll do some practice problems on them next.